Hello, today we're going to be looking at the relationship between arcs and chords within a circle in section 10.3. There are three basic theorems that we're going to focus on. The first one says that in a circle, two minor arcs are congruent if and only if their corresponding chords are congruent. If you take a look at the first picture on your notes, that means that if I know that arc AB and arc CD are congruent, then I can also assume that chord AB and chord CD, which are line segments, must be congruent as well. The converse is also true. If I know about the lengths of the two chords, if line segment AB and line segment CD are congruent, then the corresponding arcs must be the same size too. So arc AB would be congruent to arc CD. The second theorem tells us in a circle, if the diameter or radius is perpendicular to a chord, then it bisects both that chord and its intercepted arc, or its corresponding arc. So if you take a look at the second picture, we have our diameter, BA. I know it's a diameter because it passes through the center of the circle, indicated by a point. It's perpendicular to this chord, TV. Since the diameter is perpendicular to the chord, it bisects the chord, so the two halves, TU and UV, must be congruent. And it also bisects the intercepted arc. So it also bisects arc TV, so that TA and AV must be congruent. So here, since I know BA is perpendicular to chord TV, there are two things we know are true. TU and UV must be congruent, and arc TA and arc AV must be congruent. And our last theorem says, in a circle, two chords are congruent if and only if they are equidistant from the center of the circle. So here I'm looking at circle G, so here's the center. Notice that GB and GE are each marked as 10 units long. That's the distance from the center of the circle to each of the chords. So GB represents the distance to chord AC, and GE represents the distance to chord FD. Since BG and GE are the same size, the chords AC and FD must be congruent. Okay, let's take a look at the examples down at the bottom. In questions 1 through 3, it says circle O has a radius of 10. AB is 10 units long, and the measure of arc AB is 60 degrees. So let's figure out a few things based off of this information. So number one, if the radius OY is perpendicular to chord AB, and we know that it is, it shows the right angle here, that means that chord AB gets cut in half into two congruent parts, and its corresponding arc, arc AB, also gets bisected. If arc AB was 60 degrees, when it gets bisected, each half should be 30 degrees. Similarly, if chord AB was bisected, the entire length was 10 units, then each half must be 5 units. That will answer the first two questions. So the measure of arc AY is 30 degrees, and the length of line segment AX is 5 units. Question number 3 is a little bit tricky. In question number 3, they ask us for the length of line segment OX. So OX is not a radius, but it's a part of one of the radii. The trick in this question is to draw another radius so that you create a right triangle and can then use Pythagorean theorem to solve for OX. So here, if I label OX, let's just call that X, AO, the radius I just drew in, has to be the same as all radii of the circle, which we were given as 10 units. Now I have a right triangle. I'm missing one of the legs, so I can use Pythagorean theorem to solve. So x squared plus 5 squared equals the hypotenuse, 10 squared. So x squared plus 25 equals 100, which means that x squared is 75. And when you square root both sides and simplify, this becomes 5 root 3. So OX, the missing side of that triangle, is 5 root 3 units long. In questions 4 and 5, it says in circle P, the length of PD is 10 units. PQ is also 10 units. So from that information, I have two chords that are equidistant to the center of the circle. So right away, I know those two chords, A, B, and C, E, are congruent. I also know that each of those two chords is bisected because each of the radii hit the chords at a right angle. So if the two chords are congruent and they're bisected, all 4 of these little line segments must be the same size. All of that came from the first piece of information here. It also says QE is 20 units long. So now I know QE is 20, QC is 20, AD is 20, and DB is 20. So question number 4 says find the length of AB. So AB, the entire thing, 20 plus 20 must be 40. Then find the length of PE. PE is not drawn, but PE is a radius of the circle. Again, if we use the same trick as the last question, if I draw in that radius, I can use Pythagorean theorem to solve for its length. So now I have a right triangle. The legs are 10 units and 20 units, and I'm solving for the hypotenuse. So 10 squared plus 20 squared equals c squared. That's 100 plus 400, or 500, equals c squared. And when you square root both sides and simplify, this should become 10 root 5. So PE, the radius of the circle, is 10 root 5 units long. Okay, question number 6. In circle Z, PZ and ZQ are congruent. So again, we have two chords equidistant from the center of the circle. So the two chords are congruent. They're each bisected. So all 4 of these little parts have to be the same. Then it says XY is 4a minus 5 and ST is negative 5a plus 3. So those two chords have to be congruent. I can set their measures equal. 4a minus 5 equals negative 5a plus 13. When you solve for a, 9a should equal 18, which makes a 2. They asked for the length of line segment SQ. So So let's first plug back into ST. ST was -5 times A, which is now 2, plus 13. So that's -10 plus 13, or 3. If ST is 3 units long, SQ, which is half of that, ends up being 1.5. In number 7, we're looking for the length of line segment TV. TV is a chord of the circle. So to find its length, let's look at what's given in the picture. So we have 2 parts of the radius shown. US is 5 units, SR is 6 units. Together they make up a full radius. 5 and 6 would have to be 11. I'm going to draw another right triangle like we've done for several other questions, because now I know that any radii or all radii are 11 units long. And if I form this right triangle, I can solve for the length of SV. So if I do that first, let's say x squared plus 6 squared equals 11 squared. Then x squared plus 36 equals 121, where x squared is 85, and x is the square root of 85. That represented the length of SV. SV is half the length of the entire segment we need, TV. So to find the length of TV, we'll double the square root of 85. So you can leave your answer as 2 root 85, or if you prefer, this is about 18.4. In question number 8, it says solve for x if circle P and circle Q are congruent. In circle P, we're given one chord, RS, which has a corresponding arc measure of 155 degrees. In circle Q, we have chord TU. We're missing its corresponding arc measure. But I know that the remainder of the circle is 205 degrees. So if I take 360, subtract off 205 for that major arc on the left side, I can find out that arc TU, the minor arc, is also 155 degrees. Since arc TU and arc RS are congruent, their corresponding chords, TU and RS, must be equal. So 7x minus 44 must equal 3x. So 4x should equal 44, and x should be 11. Okay, in this last question, it says the common chord AB in between circles P and Q is perpendicular to the segment that contains the centers of the circle. So essentially this is saying AB is perpendicular to line segment PQ. If AB is 10 units long, what is the length of PQ? So AB is a chord of both circles actually, and since that chord is perpendicular to the radii, it gets bisected by that radius. So if AB is 10 units long, each half is 5 units long. We need the length of PQ, so let's split this into 2 different right triangles. So the first one I'm going to look at is this triangle here. I know one leg is 5 units, the hypotenuse is 11 units. I need the length of the other leg, so I'm going to call it A. Then we can look at the right triangle on the other side. That's this one. It has one leg that's 5 units as well. Hypotenuse is 9, but we're missing the other leg. Let's call it B. If I can solve each of these right triangles for A and B, I can add them together to get the length of PQ. So let's do exactly that. In the triangle on the left side, using Pythagorean theorem, our equation would say a squared plus 5 squared equals 11 squared. So a squared plus 25 equals 121, which makes a squared 96. When you square root both sides, a should be 4 root 6. Then using the right triangle on the right side, and again Pythagorean theorem, b squared plus 5 squared will equal 9 squared. So b squared plus 25 equals 81. So b squared is 56. And when we square root both sides in this equation, b should be 2 root 14. Together, A and B make up line segment PQ. So PQ is 4 root 6 plus 2 root 14. You cannot combine those terms together. They're not like terms because the radicands are different. So this would be your final answer in simplified radical form. Or if you prefer, this is about 17.3. Please make sure you complete the corresponding homework for this section. Have a wonderful day.